Professor Saumya Shankar is currently an assistant professor at IIIT-Bangalore. She received her PhD in computer science and engineering from IIT-Bhubaneswar in 2024. Prior to defending her thesis, she joined the University of Auckland, New Zealand as a research associate, later transitioning to a postdoctoral role. Her research interests include formal methods in software engineering with a particular focus on runtime verification and enforcement. Her work has been published in notable venues including Spin, RV, Time, ISEC, FMSD, STTT, and HSCC. Okay, so today we have pleasure of hearing from Professor Saumya Shankar on ensuring correctness at runtime. Thank you.
Thank you, Professor Raghuram, for the introduction. So here I am, Saumya Shankar, and the topic of today's Samvaad talk is ensuring correctness at runtime enforcement in action. So I look forward to engaging with you all, and thank you for your attention, and let's get started. So we see software and software systems in everyday life. So these examples highlight their presence in these variety of settings, be it healthcare, technology, or finance. So when we build a software system, then that undergoes through following steps. So first we write the specification of the software. We take it from customer. Customer defines that this particular software, for example, this particular banking software needs to be done. And these are the specifications which I want in my software. Okay. Then we go for designing phase, in which we plan out all the modules which will be there in the software. Okay. And then we go for coding of the software. We implement the software using some languages also. And when the implementation is complete, when the coding is complete, we go for testing of the software. So we take some test cases and then we check if the software is working fine for those test cases or not. Okay? And then that is software is deployed. And then it is also maintained for various updates. If the bank wants some updates, then that is done. So this is the traditional development cycle. Okay. So for ensuring correctness of the software system, we have this testing approach. Okay. However, we cannot test with all the values. No, testing is like viable only for trivial systems. We can test only trivial system with all the test cases. So that is why, and also this famous scientist, what he suggested is that the program testing can be only used to show the presence of bugs. So we can take some test cases and we can get to know that, okay, for this particular test cases, this is failing. However, it might be the case that I did not choose test cases properly and some bugs were not found out. So this is the limitation of testing. So that is why and also this is being done at this stage where the coding is already done. So if something is not working fine, then then the cost of changing the software, like changing the code, is a lot. That is why there is a need of including this verification approaches in the early phases before implementation. So that is why we have this verification approaches, which is done prior to this implementation or coding phase. So verification, it ensures correctness before coding. That is why it reduces a lot of cost and improve reliability. Next, so we had this verification or simulation thing, which was used to perform before the implementation. Then the goal was to verify correctness at an early design phase before implementation. Now, there are various types of simulation, which can be exhaustive simulation, in which we check for all the test cases, which is not possible for a larger system. And then we have this non-exhaustive simulation, where we take only few test cases and check the system. However, there is a requirement of even higher level confidence in the system. So we have this testing and verification, but we require a higher level of confidence in the behavior of software systems. For example, we have these incidents for the Pentium incidents, in which when Intel released one processor and then it was distributed and then some bug was found. Instead of doing the verification and testing thing, some bug was found, because of which it has to recall all the processors. And then there is another incident in which an aircraft just exploded just after 37 seconds of the takeoff. Even when the testing and verification was carried out, then also these catastrophic incidents are there in the literature. Okay. So that is why there is a need of formal verification, a more rigorous and comprehensive verification approach. So The thing is, simulation, they increase confidence but not guarantee correctness of the software. And also these days, the legislation and certification authority, they require proof of the critical properties in terms of documented verification processes. So the industry, what will they say that these are critical things, this should definitely be satisfied by the software. That is why this formal verification technique are used. So what is formal verification technique? So formal verification techniques uses a mathematical reasoning to prove the correctness of design with respect to specification. Meaning whatever we want to, the model, the system which I want to generate, we check it against some property that it should definitely specify. Okay, so what we do here is we take the system which the customer wants, and then we either take the original system or we make an abstraction of the system, and then we take the specification or the property which the system should definitely satisfy, and then we check if that is the properties are respected by the system or not. So yes, sometimes it is done on the design prototype, or sometimes it's applied on the implementation. Yes. So in order to understand what specification is, let's take an example. So this is an example which was used by my professors in my college. So it says that, okay, 3 people were standing, and they standing in Scotland, and they witnesses a cow. So one of the person, like you undergrads, they say that, okay, we have brown colored cows in Scotland. The other person who was an engineer, like Professor Raghuram, what he says that, no, we can't say this. We have to say like, there is at least one cow in Scotland which is brown in color. However, formal verification engineers like Dr. Meenakshi and Dr. Sudhit, they will correct it, and then they say that no, in Scotland at least one cow is there whose one side is actually brown. We can't say about the other side of the cow. So this is what specification means, an ambiguous description of what a program should do. So that's why we have this formal verification approaches. So one of the formal verification approaches, theorem proving, which are similar to proofs in mathematics. So you must have done proofs, no? Proof by mathematical induction and all those things, where you take a theorem and then you have a set of predefined rules, and you check if that theorem, you somehow come to prove that, okay, this theorem is actually true or not, using those inference rules. So this is similar to, so that proof is, theorem proving is similar to those kinds of proof in mathematics. Then we have conformance testing, means testing using formal methods, where what we do is that the test cases are generated from the specification, means mathematically written properties. And then those test cases are used to check the implementation. Next, we have model checking, which is a very famous formal verification techniques. What we do here is that we take the requirements of the property which the system should definitely satisfy, then we formalize it, means write it mathematically, and we take the system and generate an abstraction of the system, which is the model. And then using model checking algorithm, we check if those specifications are satisfied by the model or not, and we give verdict that, okay, the specification is satisfied by the system. And if not, then we say that, okay, this is not satisfied, and this is the trace where it is not satisfied. And then again, based on the counter examples, the engineers can again change the model, change the system accordingly. So this is done in model checking. So by studying the counter example where the trace is, where the system is not following these requirements, one can pinpoint the source of the error in the model, and then correct the model, and then again do the same thing. So this kind of very popular model checking has certain issues. For example, availability of the system model. Meaning that sometimes when the system, we can't make a model out of it. So if, or maybe because of security reasons, the engineers, they could not give us the full model. So these are the certain issues because of which one cannot employ model checking. Okay. So and sometimes also, even if you statically verify a system, you make model, you check it against properties, and then you statically verify a system, then also at runtime, one can have certain uncertainty in the environment, because of which the system is not working properly. Those uncertainty can be because of compiler bugs or mismatches of the behavior. So one thought that, okay, this software will be deployed at some platform. However, somebody else is using some other versions of platform, because of which the behavior is mismatched. or because of runtime vulnerability, like runtime attacks, the system cannot is not actually working fine. So these are the cases where this, even if we verify a system statically, it might be the case that at runtime the system is not behaving properly. Okay. So that is why there is a need of these dynamic formal verification approaches. So here what we do is that we don't, since we don't have the model of the system, but the executions of the system are with us. So we take the executions of the system and we check if those executions are satisfying those properties or not. Okay. So sorry, no, we don't have the prototype of the model here because of various reasons. Okay, because we could not have the abstraction, or because of security reasons that model was not given to us. Okay, we only can observe the executions, like some function calls and some function calls or some input output thing. Those only were observable to us and not the model. Okay, so here we don't have the model at all with us. We only have the run of the system. Now we check if those run of the system is satisfying the predefined critical policies or not. So the main thing is that here we don't have a formal model, so it is pursued as a lightweight verification approach. So there are various types of those dynamic formal runtime verification approaches. One of it is runtime verification. So what happens here is we have the properties which should definitely be satisfied by our system. So we take those property and we synthesize a verification monitor out of it. That verification monitor is instrumented with the system, and whenever the system runs, its executions are passed to this verification monitor, which will check if those executions are with respect to property or not, and accordingly give verdict yes or no. Okay, and so this runtime verification problem is actually boils down to a word problem, where we check that the execution W is an element of all the set of valid executions. And here the complexity of generating the monitor is typically negligible given small set of properties. So this runtime verification can be applied on the current execution, or it can be also be applied on the recorded execution, or for example the logs of a system. And the verification monitor, this verification monitor should adhere to some principles like impartiality or anticipation, meaning that if I am able to finally say that okay, the property is satisfied, and all the afterwards executions also will say that okay, the property is satisfied, then I should definitely give a conclusive verdict, true or false. True. If I'm not able to say right now, then I should never give a conclusive verdict. I should say that okay, in future maybe it will not satisfy. So these are the things which the monitor should take care by giving a verdict. Now, the other form of dynamic formal verification approach is runtime enforcement. So sometimes in the safety critical system, it's not only sufficient to say that okay, the property is satisfied, or the property is not satisfied. Sometimes we need to correct the behavior also. So sometimes if the property is violated, then we need to correct the traces. That's why we have this runtime enforcement approach. So where here what we do is that the traces which were coming, if they are not according to the property, if they are not satisfying with respect to the property, then we also modify it using some enforcement mechanism. For example, suppose the traces were coming and it was not satisfying the property, then the enforcement monitor can also edit those traces such that it now satisfies the property, so that we can now relay it to the other system. So it also corrects the executions of the system. So what are all the modifications done by the enforcement monitor? So in case of violation, the execution can be blocked, or maybe it can be changed to satisfy the property, or it can just wait for the newer events to come so that later it can satisfy the property, then it will be released. So these are various actions which the enforcement monitor can perform. Now, while performing those modifications, runtime enforcement monitor should always adhere to these principles. For example, soundness and transparency. So what soundness means is that when the runtime enforcement monitor changes the execution, then it should change such a way that the final output should always satisfy the property. And the second thing is that if my executions were already satisfying the property, then it should not change it. It should just relay it directly to the other system. Means unnecessarily changing should not be done. That is meant by transparency. So yeah, let's see one case study where we will use runtime enforcement approaches to provide assistance in a surgical procedure. So I am quite sure that you must have heard of minimally invasive surgeries in order to remove a kidney stone in the gallbladder, where we don't cut open the entire organ, but we make small incisions, insert the lasers or other instruments and perform the surgery there. Yeah, so we will be seeing one case study regarding that. So these minimally invasive surgeries are different from traditional or open surgeries, where the doctors will cut open the organ and perform surgery. And the problem with those surgeries are that they are quite invasive, leave large wounds, and painful. They are painful and have long healing time. And there is also risk of infections with these traditional open surgery. However, on the other hand, we have these minimally invasive surgeries. Sorry about the typo, where the doctors will make small incisions, insert the instruments, and perform surgery there by visualizing them on a big screen. So they also insert some video cameras which will capture the images inside the body, and it will be visualized on a big screen, and then they see there and then do the surgery here. So these surgeries are very much preferred over traditional open surgeries. Why? Because of reduced post-surgical complications. Now, the problem with these kind of surgery is that we have these visualization challenges, because we cannot perceive how much depth we can go inside. Like the tools don't, we can't. We have this the problems like a limited range of motion is there. We cannot move with the instruments a lot, and also we cannot see how much deep the instruments are going. So these are the problems, and also there are some technological problems also. So that is why there is a need of improved support in terms of better technologies and in terms of expert surgeon comments. That is why the surgical assistance, manual or automated, can be provided. Manual means that suppose a newbie surgeon is performing the surgery, then expert surgeon should be there, who should be visualizing everything, and then uh, uh, asking the newbie surgeons to do it, like follow the guidelines and do it properly. Or some kind of automated surgical assistance can also be provided, which will reduce the operative time and complications. And formal methods have been used to design these kinds of safety critical systems, where we can identify the inappropriate behavior. So the good behaviors or the bad behaviors, we can write it in terms of policies, and we can generate a monitor, as I showed before, and then they can be attached with the system, and whenever the system is running, it can identify good or bad behavior and accordingly give verdict. That is why in one of the framework, we employ this formal monitoring approaches for accessing a surgical procedure and giving feedback to the surgeons. So this is one of the work I did it in my PhD. We call it automated surgical procedure assistance framework. So what we did here is that, first of all, we contacted some expert surgeons and we jotted down some clinical guidelines which should be definitely be respected during a surgeries. Then those clinical guidelines we converted into, we wrote it formally, and we synthesize a monitor out of it, which will sit on the entire system and observe if everything is done correctly or not, and then it will give verdict. And on the other hand, what we did is that we collected images or videos of laparoscopic surgeries, and we trained a model which will identify in each of the frame which all tools are being used. So we did that. So this was done before runtime, before actually doing the surgeries. Now, whenever surgery is being performed, then the images captured by the laparoscope was fed to this tool identification module. It will extract which all tools are used in particular frame, and that information will be fed to the monitor. And then the monitor will check if those tool usage patterns are correct with respect to policies or not, and will give verdict. So these were three things. First of all, we trained tool identification module, and then we also wrote some policies. And at runtime, whenever the operation was carried out, we checked if the tools usage pattern by the doctors is correct with respect to those properties or not. So ML model is just used for identifying which all tools and the local were present in each of the frame, and they're also their position localization was also done. So it will just give me an array in which will say that, okay, these particular tools are there, and that tool information was fed. So if we see some example property, then it will be more clearer. For example, suppose I wrote one property saying that tool T2 should not be used after tool T3. Suppose a tool is there, indicator should never be used after specimen bag, for example. Then what I will do is that I will make a monitor out of this property, and I will just uh, uh, instrument it with this particular system. So suppose at runtime, whenever this is the tool usage pattern by the surgeon. So suppose at runtime we get this information that, okay, in this particular frame the surgeon has used tool T5 and T6, which is okay with respect to the property. So it's fine. Just let the surgeon do. Suppose tool T3 is detected in the next frame. Suppose tool T3 is detected, then the monitor will be cautious. It will check in the subsequent frames if tool T2 is being used or not. And suppose here, if tool T2 is detected, then it will flash an alert message that, okay, he has used tool T3 previously and now he's using tool T2, which is not correct with respect to the clinical guidelines. So this way the errors can be detected. And so these are some information that in this particular work we used automata, like actually a variant of timed automata, to represent those policies. So this is one of the representation of the policy. So here we see that, okay, from these are okay states, these are safe states, these are violating states. So as we see here that from a safe location, if tool T3 is there, then it's fine, it is also at a safe location. But from this location, if I get a tool T2, then this automata is going to this violating state, meaning that this should not be there. This is wrong with respect to policy. So this is the policy modeling language which we use for this particular work. So in conclusion, we employed the runtime enforcement framework for accessing a surgical procedure and giving assistance to the surgeon at real time in form of feedbacks. So the overall architecture ensures real time feedback, because the policies were very the monitor was very much lightweight. And also, instead of this module, one can also, instead of this faster RCNN module, one can also use some other modules. And that's why one can utilize state of the art trained model, which can further enhance the overall performance. And also one can add many other properties as well as and when required, so which gives the flexibility of adding complex policy. So this was all from my talk. Thank you for your patience learning. Yes. Yeah. Yes. The verdict is currently true, means the properties are not false. The property is violated. And uh, okay, so here we used runtime enforcement framework, but we did verification only. We just alerted the surgeons. Yes, we are not correcting anything. Yeah, we are just alerting the surgeons. Verification. Yeah, but then the thing is that based on the verdicts, different actions can be prompted. For example, if a lot of blood, for example, if this property is violated, then one can inform the blood bank to keep the blood ready or something. So it's just not verification, just not identifying if um, violation has taken place, but also to make uh, yes, 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 it doesn't interfere with the system right now. Yes. Yes. So yes, it has to be modeled back here. Here we have to specify the corrective actions as well, so that it does not go to this violation state. So there should be some corrective actions which keep the system in safe states only. So yes, we use the system for kind of verification only and not for enforcement, because we can't do much with this kind of critical systems. But if suppose one takes an example of autonomous vehicles or something, then one can also integrate correctness measures, for example, a hard stop or anything like that. Yes, yes, uh, yes. So it is there in the prototype. Yes. So the this particular image is being visualized on a big screen, and then one tool identification module is also integrated. That is identifying the tools at runtime, and that information is fed here to the monitor. So those things can be outside this particular system, not here, but then inside yeah. And sometimes actually in some experts were also suggesting us to have the alerts here. For example, in terms of haptic pressure or something, we can just give some pressure, haptic pressure or something to the surgeons whenever a policy is violated. So that can also be inside the system as well. So for example, a kind of vibration can be issued if the policies are violated in some tools or something.
Thank you all. Let's thank Professor Saumya for his wonderful talk. Thank you all, and we'll see you again in the next Samvaad talk.